Photoelectron spectroscopy. Generally speaking, electrons are found in shells, which we also call principal energy levels, located at increasing distances from the central nucleus. The first ionization energy, or IE with little subbed 1, of an atom of an element describes the amount of energy required to remove the outermost electron from an atom of a given element in the gaseous state. The outermost electrons are the highest energy electrons in an atom and are referred to as valence electrons. There are a number of ways that shell model or the Bohr model can be represented. Consider two versions for sodium. Now we know that sodium is Na and that it has 11 electrons. So the electron configuration would be 1s2, 2s2, 2p6, and 3s1. One way of representing this electron configuration is a model where the 2s and the 2p are separated. So we would look at this and we'd say, okay, this first ring is 1s with 2 electrons, as we see right here. But these next two rings are separated out, so you can see the 2s2 and the 2p6. So in this first ring, we just have the 2 electrons, and in the next ring, we have the 6 electrons. And finally, we have the third ring right here with its 1 valence electron representing 3s1. What you're more familiar with is the model with the second principal energy level listed as one shell. So I would look at this and I'd say, all right, this shell, this number 1 shell, is still 1s2, but this second shell right here is both 2s2 and 2p6 because we have a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons right here. And that basically takes this and adds together the electrons from the 2s2 and the 2p6 to give you a total of 8 electrons. And finally, that third shell is represented by this 1 electron right here for the 3s1. For atoms having many electrons, more energy would be required to remove an electron from the inner shell than it does to remove an electron from the valence shell. To illustrate this point, imagine we have an atom with 3 shells, N1, 2, 3, or in this case, we have 1, 2, 3, 4. Do all electrons in a given shell have the same amount of energy? Nope, not really. The explanation lies in the quantity of energy required to remove an electron from an atom. How is an atom created? A solid substance can be heated and phase changed to a liquid and then to a gas. If additional heat energy is applied to a gas, the substance can break down into individual atoms. So we start as a solid and we add some heat to melt it. Then we go to a liquid, we add some more heat to vaporize it. We go to a gas, we would add even more heat, and we would end up with individual atoms. The photoelectric effect. The photoelectric effect is the observation that photons, short-wave, visible, or ultralight light, can cause a solid substance to emit electrons. And remember, the word emit just means to release. This is an example of ionization, with the photons providing the ionization energy. When visible or ultraviolet light is shown on a substance, the energy from the photons of light excite the electrons in the substance. If the energy exceeds the ionization energy of an atom in the substance, then the electron is emitted. The emitted electrons are called photoelectrons. Energy can be applied directly to a sample such that an electron or electrons can be emitted from any shell of the atom. Note again, any shell of the atom, not just valence electrons. Cations, or positive ions, are also produced in this process. The instrument used to perform this process of creating cations is called X-ray Photoelectron Spectroscopy, or PES. In photoelectron spectroscopy, a substance is bombarded with photons, which have a given amount of energy based on their frequency. So here we have the formula. Energy of a photon is equal to Planck's constant times the frequency. Planck's constant, of course, is 6.626 times 10 to the negative 34 joules seconds. We have nu, which represents the frequency of radiation in cycles per second, and the energy of a single quantum. High energy UV radiation, or X-ray photons, are absorbed by the sample. The photons must have more energy than the ionization energy of the atoms in the sample in order for an electron to be ejected from the sample. Again, that's really important. The photons must have more energy than the ionization energy of the atoms in the sample in order for an electron to be ejected from the sample. The electron that is ejected out of the atom transforms the excess energy in the form of kinetic energy. So we have a photon coming in, it's going to remove the electron, and if the electron has excess energy after it's been removed, that excess energy is going to be recorded as kinetic energy. Therefore, the energy of the photon, which is represented as Planck's constant times frequency, is equal to the ionization energy plus the kinetic energy. Rearranging the above equation, we derive that ionization energy is equal to the energy of the photon minus the kinetic energy. With sufficient energy, an electron may be removed from any shell in the atom. Again, that's important. An electron may be removed from any shell in the atom. Using photoelectron spectroscopy, an electron from any shell, even shells close to the nucleus, can be ejected from the atom. The experimental data obtained from PES is displayed in the form of peaks, and we're going to look at a number of different ones of these and learn how to interpret them. The peaks are plots of intensity versus the energy needed to eject an electron. By convention, these peaks are plotted such that the energy represented in megajoules per mole increases from right to left on the x-axis. So my energy is actually going to increase as I go from right to left. Electrons located closer to the nucleus require more energy to eject them from the atom. So many times I'll look at this and say, okay, think of my nucleus as over here. This peak would represent electrons that are closest to the nucleus, and these peaks right here would represent electrons that are farthest from the nucleus. Consider the PES for a hydrogen atom 1s1. And we're going to say again that my nucleus, I'm going to put an N for nucleus, is over here, so keep that in mind. A hydrogen atom has one valence electron. Thus, one peak is seen at 1.31 megajoules per mole. The height of the peak is directly proportional to the number of electrons of equal energies ejected. The number 1.31 megajoules per mole tells us that it takes 1.31 megajoules, or 1,312 kilojoules of energy, to eject electrons from 1 mole of hydrogen atoms. So what does this diagram really represent? Well, this little peak right here represents 1 electron. And since we're talking about hydrogen, this 1 electron basically represents the 1 electron of hydrogen. So we would say this is 1s1. Now let's consider the PES for a helium atom, 1s2. A helium atom has 2 electrons, both occupying the first shell. Thus, only one peak is seen at 2.37 megajoules per mole. The helium peak would be shifted to the left along the x-axis compared to the hydrogen atom. This shift is accounted for by the fact that more energy is required to remove an electron from the helium atom than the hydrogen atom. In addition, the height of one helium peak is twice the height of the hydrogen peak. This difference is accounted for by the fact that helium has 2 electrons. So this is the peak that is representing helium. This represents 2 electrons here. 2 electrons. And those 2 electrons would be represented as 1s2. If we were to compare the location of this peak to the previous peak that we saw with hydrogen, we would notice that this peak is a little bit closer to the nucleus than the hydrogen was. Again, this is due to the increased nuclear charge, because in the nucleus, instead of just one proton like there was with hydrogen, there's now 2 protons. This can be better observed if both the helium atom and the hydrogen atom are displayed in the same graph. So this 2.37 represents the helium, and the 1.31 represents the hydrogen. Here with the hydrogen, we only have 1 electron, and again, that 1 electron is represented as 1s1. Here with the helium, we have 2 electrons, and those electrons are represented by 1s2. Again, as I stated before, if the nucleus is located right here, the 2 electrons that occupy helium are a little bit closer to the nucleus, because in that case, the nucleus would have 2 protons, compared to the location of the peak for the hydrogen, because in that scenario, the nucleus would only have 1 proton. Consider the PES for a lithium atom, 1s2, 2s1. There are 3 electrons total in a lithium atom, occupying the first shell and the second shells. The second shell is the outermost shell and has 1 valence electron present. Less energy is required to remove the electron from the second shell compared to the first shell. The n equals 2 electron is observed as a peak of 0.52 megajoules per mole. More energy is required to remove an electron from the n equals 1 shell. Thus, there is a peak which is twice the height, as there are 2 electrons in that first shell at 6.26 megajoules per mole, compared to the peak for the 1 in the second shell. Overall, there are 2 peaks present in a lithium atom. So this peak right here represents 2 electrons, while this peak right here represents 1 electron. And we can see, because this is double the height of this one. So this peak right here, especially since it's closer to the nucleus, would represent 1s2, and this peak right here would represent 2s1. Recall, the height of the peak is proportional to the number of electrons of equal energies ejected. In this case of a lithium atom, 2 peaks such that their relative heights are in a ratio of 2 to 1. This ratio of peak heights accounts for the 2 electrons present in the first shell and 1 electron present in the second shell. So again, like I just said, here we have 2 electrons and here we have 1 electron. Consider the PES for a beryllium atom, 1s2, 2s2. In a beryllium atom, electrons occupy the first and second shells. Less energy is required to remove an electron from the second shell than an electron from the first shell. The second shell electrons are represented by 1 peak at 0.9 megajoules per mole. So since these 2 are the same height, I have 2 electrons here and I have 2 electrons here. This peak representing 1s2 and this peak representing 2s2. Due to the closer proximity to the nucleus and the associated increase in Coulombic attraction between the nucleus and the electron, more energy would be required to remove an electron from the first shell compared to the second shell. This is observed as a peak at 11.5 megajoules per mole. So compared to helium and hydrogen, this beryllium atom has a much higher energy associated with 1s2 compared to those other 2 elements, due to the increased nuclear charge affecting these electrons in the first shell. Overall, 2 peaks of equal height are observed for an atom of beryllium. The equal height of the peaks is accounted for by the presence of 2 electrons in both the first and the second shells. Thus, the relative peak heights are in a ratio of 1 to 1, respectively. Consider the PES for a boron atom, 1s2, 2s2, 2p1. An atom of boron consists of 5 electrons occupying the first and the second shells. As previously observed, less energy is required to remove one electron from the outer second shell compared to the inner first shell. Removal of the lowest energy electron in the second shell is observed as a peak of 0.83 megajoules per mole. So this would represent my electrons in the first shell, and this represents the electrons in the second shell. Another peak is observed at 1.36 megajoules per mole for the remaining two electrons occupying the second shell, and is twice as high as the peak at 0.83 megajoules per mole. So this peak is representing one electron, and this peak is representing two electrons. There are two electrons occupying the first shell. This is observed as a peak of 19.3 megajoules per mole. The height of this peak is the same as the height of the peak at 1.36 megajoules per mole. This same peak height is accounted for by the two electrons being present in each peak. So as we saw, one electron here, two electrons here, and then again, we're going to have two electrons here. So this peak is representing our 1s2. This peak right here, which is farther away from the nucleus and less energy, is representing 2s2. And finally, this peak right here, which is the farthest from the nucleus, with only one electron, is going to represent 2p1. In a carbon atom, 6 electrons occupy the first and second shells. The PES displays 3 peaks, all of equal height, at 1.09 megajoules per mole, 1.72 megajoules per mole, and 28.6 megajoules per mole. One observes a gradual increase in the ionization energies for the center peak, the 1.72 megajoules per mole peak, in the spectrum from boron to neon atoms. This increase is accounted for by an increase in effective nuclear charge felt by the electrons in the atom. If we take these 3 peaks and we compare them to our electron configuration, this peak would represent 1s2 with 2 electrons. This peak right here would represent 2s2 with 2 electrons. And finally, this peak right here with the lowest energy level would represent 2p2 with also 2 electrons. In addition, there's a gradual increase in the energy of the electrons in the outermost shell, despite the fact that less energy is required to eject these same electrons. Once again, this increase in electron energy is accounted for by the increase in effective nuclear charge. So what exactly does that mean? We know that as we move across the period, the number of protons in the nucleus is going to increase, making the nucleus more positive. This number here of 1.09 in the boron atom was only 0.83. 0.83 is a lower value even though it's in the same 2p shell. So this value right here has increased because of the increased number of protons in the nucleus, therefore affecting the overall effective nuclear charge. Let's examine why electrons in the second shell from boron to neon occupy different energy levels. The concept of sublevels can now be discussed in terms of PES data. The largest amount of energy required to remove an electron is always highest with electrons located in the s sublevels. If we re-examine the comparison of PES data for the hydrogen versus helium, the data suggests there is only one sublevel, the 1s sublevel, present in the first principal energy level. Recall, 1 represents the principal energy level and s represents the sublevel. The data also confirms the Pauli exclusion principle, which states that a sublevel can hold a maximum of 2 electrons. An analysis of the PES data for lithium further confirms these ideas. The spectrum suggests that the third electron of an atom is added to the 2s sublevel. Thus, the electron configuration for hydrogen is 1s1, helium is 1s2, and lithium is 1s2, 2s1. Consider the spectrums for beryllium and boron. The existence of 2 sublevels within the second principal energy level explains the minor inversion in the ionization energies of beryllium and boron. The PES data suggests that it is slightly easier to remove the outermost electron from the boron atom, which is 0.83 megajoules per mole, than from the beryllium atom, which is 0.90 megajoules per mole, despite the greater nuclear charge in the boron atom. And we can see that right here. So this is 1s2, this is 2s2 for beryllium, and for boron, this is 1s2, 2s2, 2p1. Even though boron has more protons in its nucleus, less energy is required to remove this outermost electron compared to the beryllium atom with its nucleus. Trying to remove one of these electrons requires more energy than the one in boron. The outermost electron in the boron atom is in the 2p sublevel, whereas the outermost electron in the beryllium atom is in the 2s sublevel. Thus, as we move from boron to neon in the second period, the number of electrons in the 2p sublevel gradually increases to 6. The primary evidence for this observation lies in the intensity of the peak corresponding to the 2p sublevel. In terms of the peak representing the 2p sublevel, boron has a peak of 0.83 megajoules per mole, as we see right here. Carbon at 1.09 megajoules per mole, as we see right here. Nitrogen at 1.40 megajoules per mole, as we see here. Oxygen at 1.31 megajoules per mole, as we see here. Fluorine at 1.68 megajoules per mole, and neon at 2.08 megajoules per mole. The height of the 2s peak in neon is 3 times that of the boron 2s peak. This difference in peak height suggests that a 2p sublevel can hold a maximum of 6 electrons. And we can see here as we go through the PES data, here boron has 2 electrons, and 1 electron, and we can see the differences in peak height. Carbon, 2, 2, 2, the peak heights are all the same. We get to nitrogen, 2, 2, then 3 electrons. So this peak right here represents 3 electrons relative to the s sublevels. Oxygen is 2, 2, 4. So this final peak out here is double in size to the 2s sublevel right here. Fluorine is 2, 2, and then 5 electrons. And finally here, 2, 2, and 6 electrons, where this peak right here is triple in size of the 2s sublevel. Thus, the electron configuration for a boron atom must be 1s2, 2s2, 2p1. The carbon atom must be 1s2, 2s2, 2p6. The nitrogen atom is 1s2, 2s2, 2p3. Oxygen is 1s2, 2s2, 2p4. Fluorine is 1s2, 2s2, 2p5. And finally, the neon atom is 1s2, 2s2, 2p6.